Welcome back to our week 12 of graduate statistics. We are today discussing correlation and regression analysis. We have been focused on the problem of predicting poverty from percentage of high school graduation in a particular place. And we started by doing just a correlation analysis, graphing, describing the relationship using a scatter plot, determining the direction of that relationship and the strength of that relationship, both through the analysis of the scatter plot and through numerical analysis, actually computing the correlation coefficient R from our sample. And then we learned that we will have to determine if that coefficient is large enough to dismiss the null hypothesis that the correlation in the population is zero. And then we moved on to discuss regression analysis, which is a step further in describing the relationship between two variables, because it literally is modeling now the relationship using a line, where with the equation of a line in hand, we can actually say by how much we can expect poverty to change given changes in high school graduation. So we ended up with a regression equation that looks like this. It has an intercept and a slope, and the slope is telling us that for each unit change in high school graduation, here percentage, if high school graduation changes by 1%, percent poverty will change by 0.62%. All right? So we know by how much to expect change in poverty given changes in high school graduation. Again, regression does not allow us to make causal inferences. We know, that that's the kind of relationship that's out there. If there is no causal relationship, it doesn't mean that, okay, so let's intervene and increase high school graduation and to see if poverty increases. That would be the kind of research that would allow us to establish causal relationships, because it may or may not be there, right? The kind of observational data we're dealing with only says that the two things change together and they change in opposite directions. We cannot for sure say that if we change graduation, the amount of students graduating, we will change poverty levels. It is a hypothesis to be tested through intervention. All right. Having said that, then we moved to the idea of prediction, trying to figure out what poverty might be given that we know what high school graduation is. Why would you want to do that? Well, if you have this in hand, it may be the case that in your data set, you don't have a particular value of high school graduation in hand. But in your city in the United States, you want to know, we have about 20% of high school graduates. What is the expected percent poverty in our population? We can actually plug that percentage here, multiply by this, and then subtract from here to get to percent poverty, right? So this is the exercise we're doing, right? So prediction. If I know a value of high school graduation, how can I know what poverty looks like? So according to we'll do this exercise now of prediction. That's where we stopped. And according to the following linear model, what is the predicted percent living in poverty in states where high school graduation rate is 82%? So here is the relationship. Maybe I don't have a value of high school graduation that is exactly 82, but I can use the equation to actually figure it out, right? So what do? Well, I plug in 82 in place of high school graduation, and I do the calculations, and it turns out that the prediction is that it will be about 13.84. All right, that's the prediction from the model. What is the difference between prediction and extrapolation? Extrapolation is applying a model to estimate. I reverse here. Applying a model to estimate values outside of the realm of the original data. That's what extrapolation is. Let's see what I mean in a figure here. Imagine that our cloud of data is varying between about 70% of people graduating from high school all the way up to, I don't know, 95%. But you decide to try and investigate what happens, how much is the poverty rate expected if you had 20% graduation. And imagine we just have this linear model that we fit through our data, right? That's the model that we just fit. If I take 20 and go here and I'll say, oh, the poverty level will be above 50 using the model. The issue with that is that 20 is not in the range of our data, and there is no guarantee that the relationship will continue to be linear all the way, or if the relationship would be more curvilinear-like at those ranges. There is no way of us knowing that. So if you're trying to predict things that are outside of the range of your data, that have values of your explanatory variable that's outside of the range of your data, what you're doing, you are extrapolating, all right? Which means you need to be really careful because you can't guarantee that the relationship will be linear across all the range of the explanatory variable, all right? It could go really differently and then your prediction would be really off. And just to note that sometimes the intercept might be an extrapolation, which is the case of this data set, because we do not imagine zeros here, 0% graduates. We don't have 0 in our data set, so we have to extrapolate the line to figure out the intercept. And again, it's just a trick to move the line up and down to minimize those deviations, all right? It's not really meaningful in a lot of situations, like here, because we don't have 0% graduates in our data set. Now, what is R square? Sorry, let me track back. So we fit the line and we have these deviations from the line. And it would be good to know, how well did the line fit that data set? How much of that deviation was I able to minimize picking the right line, right? Because no matter what you do, sometimes you won't be perfect with real data. All points will not fall in the line, no matter how much you mess around with it. There will be some deviations. And the amount of that deviation will be a reflection of fit. The lesser the deviation, the better the fit. And you can compute a measure of model fit, which is R square. It's the squared, how you compute it, it's the square of the correlation coefficient. And that gives us the strength of the fit of a linear model. And again, it's calculated just as a square of the correlation coefficient. You just square it. And it tells us what % of variability in the response variable is explained by the model compared to how much it's not explained, right? The deviations from the line. And if it's not ringing a bell, I'll try to make it ring a bell because you've seen this before in ANOVAs. Because ANOVAs have behind the same general linear model that we use for regression. So imagine you have the total variability. Remember, we had it in vocabulary scores. Here we have the total variability in poverty. And then we'll have the amount of variability that can be explained by graduation. And the deviations represent the variability that's attributed to other factors other than % of high school graduation. All right? And R square is a reflection of that ratio, the % that is explained by our variable. Always between 0 and 1 as well, right? Because it's the square of R. If R is between 0 and 1, R square will also be between 0 and 1. So to see if you understood what R square is, what this model fit means, I don't know where I put myself here. Which of the following is correct, is the correct interpretation of the R square for this model for predicting % living in poverty from % high school graduation rate? So the R square for this model is 0.5625. So what is the correct interpretation? A, 56.25% of the time, % high school graduates predict % living in poverty correctly. That's not it. 43.75% of the variability in the % residents living in poverty among the states is explained by the model. No idea why that would be, right? 1 minus this. No. 56.25% of the variability in 56.25% of the variability in the percent of high school graduates among the states is explained by the model. What are we trying to explain? We're trying to explain poverty, right? And we put in as predictor percentage of high school graduates. So 56.25% of the variability in percent of residents living in poverty among the states is explained by our model, which has as a predictor percentage of graduates among the states. So D is the correct interpretation. All right, model fit. If the R-square for the relationship displayed in the scatter plot below is 92.16%, what is the correlation coefficient? Just the highest square root of that, right? So if to calculate the R-square, I square the correlation coefficient. To calculate R from R-squared, I just take the square root. Let's play around with a second problem when we come back. So I don't want to make this too long. When we come back, we start this another inference problem for linear regression, just as an example. Okay, see you then.